That's why I'll tell you. This is the sum of the reciprocals of the squares. Right, so you sum over all k, sum of 1 over k squared. The Basel problem to determine the value of this sum. Now, of course, anytime you have a sum, you should ask about convergence. The sum does converge. You could use the integral test, for example, from your calculus class to determine that. Historically, this was computed to be about 1.644934 and so on. But this was considered an important problem to determine the exact value. The first person to give a guess for the exact value was Euler. And that was in 1734. Okay, you might notice I wrote out an outline of what I'm talking about. A Euler solution, a Fourier analysis solution, a simpler solution, and then an application. And I put Euler's solution in scare quotes. That's because what Euler did was really just a guess, I would say, at the correct answer. He did get his guess correct. To arrive at the exact value of this summation, Euler, he was 28 at the time, made a name for himself when he gave this quote unquote solution. To give this solution, he used a very advanced mathematical technique. This is a technique I use in my research a lot, actually. This advanced mathematical technique is known as wishful thinking. So, what was the wishful thinking that Euler hoped? Euler said maybe power series behave like polynomials. Okay, well, let's see what I'm talking about. So, Euler considered the power series of sine of x over x. Now, you'll remember from your calculus class, you know the Taylor expansion for sine of x. So this is, let's see, x minus x squared. Sorry, I'm doing x over x cubed over 3 factorial plus x to the 5th over 5 factorial. And then there's more terms. Then we have divided by x, which is multiple at all these terms. 1 minus x squared over 6 plus x to the 4th over 120 and there are more. Okay, so when Euler hopes that this behaved like a polynomial, what do I mean by that? Recall that for polynomials, you can write any polynomial as a product over its roots. So for example, if I have a polynomial p of x, say in degree 3, and I say that p of x has roots 7, 8, and 9, then you know that p of x is equal to some constant times x minus 7, x minus 8, x minus 8. All right, so given any polynomial, you can write it as a product over its roots. In our case, it's going to be, I'm going to write it in a slightly different form that's more convenient. So we'll write 1 minus x over 7, 1 minus x over 8, 1 minus x over 9. Or some other constant. And you can verify you just factor out comes out of here. This is an equivalence form. Okay, so if power series behave like polynomials, then we should be able to write this power series as a product over its roots. So let's ask the question: what are the roots of this function? Remember back what the function sine of x looks like. It has roots at 0, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, so on. Canceling out one of the roots, the root at 0 by dividing by x. This has roots at plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so on. So Euler, all right, yes, here. The guess should that be correct, but anyhow, so Euler guessed that this should look like some constant c times, and then we'll write it as a product of roots. So x, 1 minus x over pi, 1 minus x over negative pi, 1 minus x over 2 pi, 1 minus x over negative 2 pi, and you can keep going. Right, and then here. Notice that you can pair up these terms as a difference of squares. So this is this constant times 1, and let's see, we have minus x squared over pi squared. 1 minus, and then about x squared over 2 pi squared. And you'll keep going, so more terms to the product. The whole reason we were doing this is we can then compare coefficients with the two power series expansions. We have this power series expansion, we have this power series expansion. So let's compare terms. Let's write out what the 0th term here is and what the second term is. So if you look at this product, you have c times 1 times 1 times 1. That's the only way you're going to get a x to the 0 term. Right, so a constant term, and people are looking. So maybe I did this already. Pull out this factor of c, and then extracting out the constant term with the mention this is 1. And then let's extract out the x squared term. We'll have higher order terms. Okay, how can you get an x squared out of this product? That means you have to take one term with the x. Yeah, for one of these terms in the product, you need to take the second term, and all the rest you need to select the ones. So 1 times so x squared over pi squared, and then select all ones. X squared over 2 pi squared, and then select all ones for all the other terms of the product. You end up with coefficient for x squared would be -1 over pi squared. Plus -1 over 2 pi squared plus -1 over 3 pi squared, and so on. Okay, with this expression, we can then compare coefficients, and you'll see where the Basel problem is coming in. This is already taking the form of sort of what we want. So first question we should ask is, what is the constant out front? What's c? There's a really easy way you can tell what c is. Compare these two. By comparing the constant term is c here, constant term is 1 there. So c has to be 1. I'll go ahead. Right, and then comparing the x squared term, we have the -1/6. It's the coefficient right there. And then this is equal to, and I'll pull out a -1 over pi squared. -1 over pi squared times 1 plus 1 over 2 squared plus 1 over 3 squared, and so on. And then multiplying both sides by -pi squared, you get that pi squared over 6 is equal to this summation of variables. So this means that Euler's guess was pi squared over 6. And this turns out to be the correct answer. Now, Euler was more or less satisfied with this argument because it matched up the numerics, right? So the numerical value that I just erased, 1.644934. If you calculate pi squared over 6, match that. So he said, well, that has to be right. What else could it be? And people generally accepted that as the solution. But I mean, of course, we have this major gap right here of this guess that the power series actually behaves like a form. I will very briefly mention another approach you could use to solve the same problem using Fourier analysis. I'm not going to spend very much time on this because I suspect that a lot of you have not seen too much Fourier analysis before, but I just want to mention this so you're aware that there are more modern techniques. So we're going to use, from Fourier analysis, we're going to use Parseval's identity. This identity says that for, I'm not gonna explain every single piece of here. We have for f certain functions f, with the norm squared of f is equal to sum of all the Fourier coefficients absolute values. Okay, how should you think about this? If you haven't seen any Fourier analysis before, you can think of these as coefficients for orthogonal basis that you're writing f in terms of. When I say it like this, then now this is a generalization of the Pythagorean theorem, right? So in the Pythagorean theorem, you can write the hypotenuse of a triangle is orthogonal legs, and then you have this identity. Same thing here, sort of. And then with this, you can calculate Parseval's identity with f of x equals x over the interval 0. Yes.
It's like an orthogonal base, like a sine cosine thing.
Yes, but I'm going to use complex exponentials. I think cosine and sine would be maybe more useful. Well, my understanding is the engineers like to write it in terms of cosine and sine, but I think it's more naturally mathematically stated as complex exponentials. But they would be equivalent. So how could you calculate this? You can calculate the Fourier coefficients f hat of k. I'm not going to go through the computation, but Fourier coefficients are 1/2 at k equals 0. And they are I over 2 pi k over k non-zero. And then the norm squared of f. And in this space, the norm squared would be integral from 0 to 1 of f of x and that's conjugate of x. In this case, integral from 0 to 1 of x squared dx, which is just 1/3. So we can calculate the norm squared of f, and then the other side of the identity. This means that we have 1/3 is the norm squared of f, which is equal to the summation . Right, and then you can pull out the 1/2 term. This would be 1/4 plus the summation of k not equal to 0. And then we have 1 over 4 pi squared by k squared. And then you can see where the Basel problem comes in. All right, so again, we have a summation 1 over k squared, and then you rearrange some stuff and you get that sum k greater equal to 0, or k greater equal to 1 over k squared is absolute. All right, I went through that really fast because that wasn't really what I want to emphasize. But I just want to say there is a way you can do this doing Fourier analysis. And it's kind of clean, but it also involves a lot of sort of background setup, right? There's a lot of theory hiding behind this that I haven't told you about Fourier analysis. So this is probably unsatisfying for a lot of you. I mean, it's unsatisfying for me if I don't know Fourier analysis, that you just pull this magic formula out of the hat. Another reason this is sort of unsatisfying is both these approaches, this summation sort of comes out of nowhere, right? We didn't really start with the summation, start working towards something. So like, it doesn't seem particularly well motivated. Certainly you admit, whoever came up with this had to be clever, but did I really understand like a good problem solving process here? I'll also mention that if you read the abstract of my talk, I said I would focus on giving a more elementary proof. And I don't think we can call this elementary if, as far as my understanding is Fourier analysis, it's considered a graduate school topic. And I said I was going to do this at an undergraduate level. So let us forget these approaches. We're going to do a new approach. All right, I'm going to erase all this. This is what I have as the simpler solution. This will be the main content of my talk. I want to talk about a simple solution to the Basel problem. Now, what is my definition of simple? I'm going to say I don't want to use any advanced techniques. So what do I consider to be an advanced technique? I want to solve this problem. I want to motivate how you could solve this problem if you're let's say a freshman student in calculus. Let's say an engineering major. Now, you'd have to be a pretty clever student in calculus one, but we'll say for the sake of argument that I'm only using. I'm gonna only use techniques that would hypothetically be available to someone with that background. And I especially also want to motivate sort of the problem solving process here. How you can sort of play around with this problem and come up with something that works. Although, of course, it does require a good bit of cleverness as well. That is true. There's no way around that. Okay, so I'm putting on my hat, tell a story of a freshman engineering student in Calc 1. You want to solve this problem, sum 1/k². Now, as an engineering student, what else could we use except for, of course, the fundamental theorem of engineering? Right? You all know the fundamental theorem of engineering? Sine of x equals x, right? We all know this, right? I'm told that's useful in engineering. I guess you'll have to ask the engineers here about that, but in any case, what happens if we instead do 1/sine² k? So instead of talking about k, we'll replace it with sine of k. How do you feel about this? Is this any easier? I see thumbs up. Okay. This is the part where you actually answer my questions. How do you feel about this? Okay, that's good. It looks horrible. Do you see any problems with trying to compute the summation? I don't think this converges. That's one problem. Right, because sine is going to vary, sine squared is going to vary between between 0 and 1, but it should be 1 pretty often, right? So these terms are not tending to 0. This is definitely not going to converge. I'm going to show you guys a really advanced technique for how you can fix convergence issues with any sum. You make it finite. Wow, right? Do I get applause for that? Like that's impressive. I can fix any convergence issues just by making the sum finite. Now, is this any easier to solve? I mean, we'll see, I guess. Any other issues you see with this sum now? I'm supposed to be solving the Basel problem here. Do you think this is a good approximation for the Basel problem? Let's say we take n really large. That doesn't look like a particularly good approximation for k². Right? So when does the fundamental theorem of engineering hold? Right, you have to pick small angles. So, I'll show you another very advanced technique. How do you make angles smaller? You divide it by a big number. Like right now, already this is a much better approximation. Let's see. Now, the reason this might have some hope of being easier to solve is we have all sorts of trig identities we can use. Right? 1/sine², that should be some trig identity for something, right? So if we're going to use trig identities in this, we should probably be plugging in actual angles. Does k/n look like an angle to you? Not really. All right, well, I'll show you another really advanced technique. Here's how you make it an angle. Multiply by pi/2. Now this is an angle, right? Okay. All right, let's see. We're getting further and further away from the Basel problem, but that's okay. Well, we'll keep going. Let's see. For convenience, it's going to be nice if n here is a power of 2. So I'm going to make one more modification. So there's pi/2 and k. I'm going to do up to 2 to the power of n. Like this. Close my braces. All right. One last thing. This summation is going to be most convenient to work with if it's symmetric. Notice what these angles are ranging between. the angle range between pi over 2 times 1 over 2 to the n up to pi over 2. So for symmetry, it's going to be slightly nicer if we omit the last term, right? And then both ends are non-inclusive. Okay. I'm done modifying. This is now the sum we're actually going to compute. So we'll call this a sub capital N. Now, does this have any hope of behaving like the Basel problem? Actually, yes, because the only terms that really matter in the Basel problem are the first few. Right, these terms go to 0 pretty fast. So if you want to approximate, only the first couple terms matter, and that's precisely where sine squared is a good approximation. Okay. We're going to use an inductive type argument, which means we're going to have to relate this summation to the summation for a sub n plus 1. So I'm going to write a sub n. This is sum, it goes from 1 up to 2 to the end, times 1. 1 over sine squared, pi over 2, k over 2 to the n. And then this is equal to, all right, so if we're going to rewrite this in terms of a sub n plus 1, think about what the angles would be at a sub n plus 1. The angles would be pi over 2, k over 2 to the n plus 1. I'm going to write this 1 over sine squared 2x, where technically x should have a subscript of n and k, but this is very temporary. Right, where x is pi over 2 k over 2 to the n plus 1. Right, so x is the actual angles I want to use for the a sub n plus 1 summation. I can write the current summation a sub n is 1 over sine squared 2x. Okay. Then off to the side, let us recall an identity for that might not be enough. I'll do it over here. 1 over sine squared 2x. Who remembers their double angle formula for sine? Nobody, all right. I wanted to have either. I thought that compared to tough. Sine squared of 2x, or let me just say sine of 2x is 2 sine cosine. Okay, so this is the squaring, this would be 4 sine squared x cosine squared x. Now I want to break this up into terms that look like this, which means I'll use Pythagoras on the top term, on the 1 here. So this is 1/4 sine squared x plus sine squared x over sine squared x cosine squared x. Okay, now we're going to do this is 1/4. Right. We have cosine squared over sine squared cosine squared. Let's take 1 over sine squared x. And then this term becomes 1 over cosine squared. Already, this is looking encouraging, right? We kind of wrote something in terms of 1 over sine squared, which is exactly what we'll need for the a sub n plus 1 summation. So this becomes summation. It goes from 1 up to 2 to the n minus 1. And then this is 1/4. Hold on. 1/4. This is 1 over sine squared x plus 1 over cosine squared x. All right, let me write back what x is. So this is 1/4 summation. It goes from 1 to the n minus 1. 1 over sine squared. And then this angle would be pi over 2 k over 2 to the n plus 1. And then we have 1 over cosine squared of pi over 2 k over the n plus 1. Right, so we have this big summation. Now, at this point, I think it's helpful to draw a little bit of picture about what we're trying to show. So think about this summation a sub n. Think about the angles that we're plugging into sine here. we're ranging k from 1 up to 2 to the n, non-inclusive on both ends. Then the angle here is ranging between, let's see, 0 and pi over 2. Okay, so if we draw a picture, we're done with this idea. We draw a picture of what angles we're plugging in the sine. So let's see, so that's the sine function. And from 0 to pi over 2, so I'll write this equally spaced. So we're plugging in like angles, equally spaced points over 0 to pi over 2. That makes sense. That's the angles we're plugging in. So it's like we're sampling sine at equally spaced points like this. And then think about what's happening right here. We're sampling sine and we're sampling cosine at equally spaced points over what interval? Let's see, we're going from k goes from 1 up to 2 to the n minus 1. So that means at the f-bound k over 2 to the n plus 1, that would be 1/2. So this means we're sampling angles between 0 and pi over 4. So if you draw what's happening, we are sampling, so this is cosine, this is sine, and then the angles we're choosing, these are equally spaced points over the interval from 0 up to pi over 4. I guess these should be ground credits, I guess. Not inclusive. So we're sampling and so up to here, and then points up to here. That's up to 5. Okay, so our summation here, the original summation looks like this. And here, we're summing over sine squared of all these angles and adding on to that cosine squared of all these angles. So when I write it like this, maybe it's clear what we should do now. I hope it's clear. Right, so if we're sampling at all these points, if we just reflect across, we can do this as a summation over from 0 to pi over 2. Right, because all these values we're sampling, it's same value as if we sampled on this curve from pi over 4 up to pi over 2. Which means we need to use the identity cosine of, we need to use cosine that is sine of pi over 2 minus x. I mean, that's what we need to replace in the cosine in order to reflect these across. So we can combine them into this. All right, so I'll keep going. The summation. This is the equal sign is from over there. So we have equals 1/4. And then we have sums, k goes from 1 2 to the n minus 1. So 1 over sine squared of pi over 2 k over 2 to the n plus 1. And add on to that right now we're doing our transformation to cosine. Cosine x is we're going to replace that with sine of pi over 2 minus x. Sine squared pi over 2, and then this is 2 to the n plus 1 minus k over 2 to the n plus 1. Make sense? And then when I write it like this, you can see what are all the angles. Well, I'll do it in 2 steps. So we'll write that as 2 summations. So there's a sum division 1 of 2 to the n minus 1, 1 over sine squared pi over 2 k over 2 to the n plus 1. And then we have another summation, which is summation over sum k. Or you can go ahead and write this expression. Sine squared pi over 2 k over 2 to the n plus 1. Okay, so here think about what natural numbers are being plugged into the numerator. So what should this summation run over? let's see, if we go from 1 up to 2 to the n minus 1. Then, so for those values of k, the expression 2 to the n plus 1 minus k. This will run over all values, 2 to the n plus 1, all the way up to 2 to the n plus 1. And then from there, it's clear what we can do, right? So these are the exact same expression. We combine this into one sum. This is 1/4 summation of k goes from 1 up to 2 to the n. 2 to the n plus 1. 1 over sine squared of pi over 2. K over 2 to the n plus 1. And then let's see, so this is the entire summation. Notice we're actually missing one term, we're missing the k equals 2 to the n term. Both of these endpoints are non-inclusive. So this would be, let's see, we need to subtract off 1/4, we need to subtract off that term. This would be 1 over, and then sine of this angle squared. So it's the sine of pi over 2, or it's pi over 4, sorry, yeah. Plugging 2 to the n here. Pi over 2 times a half, pi over 4. Sine of pi over 4, you remember, is root 2 over 2. That's okay. And then that would be 1/4. This is exactly a sub n plus 1/4 a sub n plus 1. And then minus so if I factor out 1, this expression is. Then rearranging, I get that a sub n plus 1 equals 4 a sub n plus 2. All right, take a deep breath. Just did a lot of computations. From here on out, it's not so technical. Technically, everything I've done is elementary. It's just a little bit messy. After all that work, we came up with this expression for a sub n. Right, so we have a recurrence relation, which means we can solve it. So you can compute a sub 1. Let's see, go up to 2. So you just have the k equals 1 term. And then let's see, plugging in n equals 1. That'd be pi over sine squared pi over 4, so that'd just be 2. A1 is 2. And then you can use this recurrence relation. 4 times the previous term plus 2. So this would be 4 times 2 plus 2 is 10. A sub 3, 42, you can go. Right. So this expression for this starting point tells you exactly what all the values of a sub n are. Now back to our story. I was supposed to be giving this story as a freshman engineering major in Calc 2. And unfortunately, or no, in Calc 1. So unfortunately, for purposes of my story, engineering majors are not taught linear recurrence relations anywhere, as so far as I'm aware of. At Clemson, I believe you might learn this in a discrete math class. But engineering majors don't take that, I think. But computer science majors are required to. At least that's what it said when I looked it up online on the Clemson course catalog. So we'll say that this engineering freshman has a computer science roommate that knows how to solve these things. And his roommate tells him that a sub n is 2/3 4 to the n minus 2/3. Now, of course, his roommate had to get to class. He had a programming assignment due. So he didn't have the time to explain the proof of this formula. But the good news is, with the information we have, even though we don't know how to come up with it, at least we can prove that it's true, right? You can do an inductive argument, right? So the first term matches. A sub we plug in 1. 2/3 times 4 minus 2/3. Let's see, 8/3 minus 2/3. Yep, that's 2. So this works out the first term, and you can also verify it satisfies the recurrence relation. So a sub n plus 1 is 4. A sub n plus 2, which is 4 times, let's see, 2/3 4 to the n minus 2/3 plus 2, which would be 2/3 4 to the n plus 1, and then minus 2/3. which is the claimed form. All right, so we can prove just by if we're given the formula first, we can easily prove that that is the correct identity. Okay, we have an expression for a sub n. Now let's go all the way back to the Basel problem. I'll leave this up right here. And we know that a sub n is 2/3 4 to the n minus. If we use the first order Taylor series approximation for sine, this would line up for the Taylor's with the Basel problem, at least up to a finite cutoff. But then you have some error terms to worry about. So, of course, as a freshman engineering major, you don't want to deal with that. So you go find a senior in the math department. And that's exactly what he tells you. He says, you know, you can use a Taylor series, and then let's see, there's some error terms. And then he starts mumbling something about epsilons and deltas. But then he starts getting worried about like exchanging limits, because we're gonna have to take a limit of this. And you realize, you know, all of this is kind of silly, because, you know, why would they call them error terms if they weren't negligible? So why would you do all this work just to show an error term goes to 0 when you already know that's the case? So we're gonna do something simpler. We are going to use, I guess what some people would call the squeeze theorem. So let's see. We're going to use this bound. So recall that for x between 0 and pi over 2, and that's all the angles we care about. For x in this range, let's see, we have tangent of x. Yeah, so x lies between sine and tangent, which means that 1 over tangent squared x plus or equal to 1 over x squared, which is less or equal to 1 over sine squared x. And this is how we can approximate what we want. This 1 over x, or yeah, we have 1 over sine squared x. That's how we can relate it to 1 over x squared. Right, I see a tangent here. I don't really want to deal with tangent. I could go through all the same work to derive a similar expression for tangent, but that would be, no, I'd run out of time pretty quickly. And already, yeah, I see I'm running out of time, but that's fine. So let's see. So we can use a trig identity here. Anybody know the trig identity for 1 over tangent squared? Pythagoras. This is 1 over sine squared x minus 1. Which is great, because we know we have an expression for 1 over sine squared x. Okay, so because of this, we have that. With using this expression, sum of k goes from 1 up to 2 to the n minus 1 of 1 over sine squared pi over 2 k over 2 to the n. So that's 1 over sine squared, and then we get minus 1. This is less than or equal to times k goes from 1 to 2 to the n. But writing here 2 to the n minus 1, and then 1 over, and then this expression squared. So pi over 2 k over 2 to the n expression squared. Well, and then this is less than or equal to the same summation over the times. K goes from 1 up to 2 to the n minus 1. 1 over sine squared pi over 2 k over 2 to the n. Right, so I'm just plugging in this identity, 1 over sine squared minus 1 over sine squared x minus 1, 1 over sine squared x down 1 over x. So plug that in here, which then means that we have an expression for this. So this is, let's see, that's 2/3 4 to the n minus 2/3. What's that expression? We also have this summation. So this would be minus 2 to the n minus 1. You're adding up 1 that many times from there. This is less than or equal to, and then I'll leave this as it is. This is sure, yeah, I can. Okay, goes from 1 up to the n minus 1 over I over 2 a over 2 to the n squared. It's going to be 2/3 4 to the n minus 2/3. Divide all sides by 4 to the n. And you end up with 2/3. And then let's see, we have minus 2/3 minus 2 to the n minus 1. All this is divided by 4 to the n. And then the reason I'm multiplying by, or sorry, dividing by 4 to the n is to get rid of this piece. So this is, so this goes from 1 to 2 to the n minus 1. And then this just becomes 1 over pi over 2 k squared. So let's make it 2/3 4 2/3 minus 2/3 over 2. And then at this point we can take a limit as n goes to infinity. Right, so notice this expression goes to 0, right? 4 to the n goes to 2 to the n. This goes to the Basel problem up to a constant. And this goes to 2/3. Means that after limiting, we get that summation k goes from 1 up to infinity of 1 over pi over 2 k squared is equal to 2/3. Then multiply both sides by pi squared over 4. We end up with the desired result. Basel problem, k greater than or equal to 1. It's consistent. K greater than 1 over k squared is pi squared. So that is my elementary proof of the Basel problem. I guess you can judge whether you think it's realistic that a freshman engineering student actually came up with that. But I will say a high school student came up with that, so maybe it's not so unrealistic. So anyways, that's I really like this this solution because although you can use a lot more elementary or a lot more advanced techniques, if you're willing to be clever enough and work hard enough, you can come up with a desired solution. We have enough time that I'm going to give one application to this. So this is the last section of my talk. And at first, it seems like an unrelated application. Given two random natural numbers m and n, what is the probability that m and n are co-prime? Take two random natural numbers. How likely do you think it is that they'll be co-prime? Anybody have any intuitive guess? Like, do you think this is very likely? Do you think this occurs like 0% of the time? Maybe you think this occurs 100% of the time? Maybe 50-50?
You say random natural numbers.
Okay, so to be precise, you need to take a limit as x goes to infinity of m and n less than or equal to x, to be very precise. But that is the way you would formulate it. I don't know if it's necessarily that helpful to like think about it like that. It's I'm being accurate. I'm giving you the right idea when I say pick two random numbers. Just, you can think of a super large amount. So how often do you think integers are co-prime?
Is there a log involved in this?
A log, you think there's a log involved? Well, do you think very likely or not so likely? Think like. Any guesses? Dr. Quicken, Dr. Quicken, thinks 2 layers.
Is it 6/5²?
It does end up being 6/5. I asked some other people earlier, they thought it was like 1% likely. Alright, so how do you come up with this? So I'm gonna work fast because I don't really have a whole lot of time. Let's see. So this is actually not too bad to compute. So probability that we're interested in. Okay, so for m and n to be co-prime, what does it mean to be co-primes? Means there are no primes that divide both m and n. Okay, so we need 2 to not divide both m and n. We need 3 to not divide both m and n. And we need 5 to not divide both m and n. Okay. So this is going to be a product over all primes p. And then the probability that we do not have the case that p divides m and p divides n, using evident measures. Which of course is product of all primes p of 1 minus the probability that p divides m and p divides n. You pick 2 random natural numbers. Well, let's say if you pick a random natural number m, how likely is it that p divides m? 1/p, right? How likely is it that divides 1 over, or that p divides n? Also 1/p. So this is 1 minus 1/p. Now, to Dr. Macaulay's point, of course, to be very precise, you should be doing this as a limit over x, but I'm morally giving you, I'm not blunt. Like this is morally what happens. Okay, so we have this expression. I'm gonna have to go over here. So this means that 1 over the probability. Actually, let me give myself more space. 1 over the probability is equal to the product over primes p of 1 over 1 minus 1 over p squared. What does that look like? It's a geometric series, right? This is product over primes p, 1 plus 1 over p squared plus 1 over p to the 4th plus 1 over p to the 6th. Plus dot dot dot. Now I'm going to write this out in hopefully a way that will make the next step more clear. So I'm going to write out a couple times. This is like 1 over 1 squared plus 1 over 2 squared plus 1 over 4 squared. All right, so you have the term involving p equals 2. And you have the term involving p equals 3, so it's 1 over 3 squared, 1 over 9 squared. And then you have 1 over 1 squared plus, I know that's 1 over 5. And then you see why I decided to have a little bit more space here. And you keep doing. Okay, now think about expanding this product. You're going to expand this product, you select a term from here, select a term from here, select a term from here. This is going to be a giant summation of 1 over some things squared. Okay, what is going to be, what goes inside this parentheses? In other words, which natural numbers appear when you expand out as a term, when you expand out this product? Okay, well, that would be every natural number that can be written as a power of 2 times a power of 3 times a power of 5, and so on. Which natural numbers can be written in the form a power of 2 times a power of 3 times a power of 5, or if you want to write it like this, which natural numbers can be written as 2 to the a, 3 to we will say a2, 3 to the a3, 5 to the a5, dot dot dot. Right, because this is what a general term would look like. You're taking power of 2 times the power of 3 times the power of 5. Which natural numbers can be written in this form? All of them. And each of them exactly once by a fundamental theorem of arithmetic. Which means that actually this summation runs over all natural numbers. Which we just solved. So this is pi squared over 6. Which means that the probability, so we were just calculating 1 over the probability. Probability is 6 over pi squared, or about 61%. So if you pick 2 random natural numbers, 60% chance, 61% chance they'll be co-prime. Which is kind of interesting. The end.
Any questions?
Doesn't the second fundamental theorem of engineering, which is that pi equals 3, tell us that that's actually 2/3 instead of 61?
Good one, yeah, right. So, you know, I can always correct. Wow. Good enough.
Well, I've been
You're both
in
right.
Indiana.
Correct.
Other questions?
Yeah, so if you compare, you compare other coefficients between their expansions to get other identities for some last.
So say that question one more time.
Yeah, so Euler's solution is to compare the coefficients of
Right.
S squared with expansions. Can you compare some other coefficients and have both?
Yes, you can. You can use Euler's solution to show that, oh, I did not. Using the exact same argument, you can show that zeta are 2k, okay, now, after all this time, now's the first time I mentioned zeta. So sum of k equal 1 over k 2m. So it's consider any even power. I was considering little n equals 1, so 1 over k squared. You could do 1 over k to the 4th, 1 over k to the 6th, 1 over k to 8, any of those. By the exact same argument as Euler's. This is a rational multiple of pi to the 2m. Of course, the question then you should ask is, what about 1 over k cubed? Is that a rational multiple of pi cubed? This is the Avery constant problem, and it's still open. Nobody knows. So Avery's constant is the summation of with cubes. Nobody has a closed form, so.
Also, do a lot of things with that Fourier transition character of different functions.
Any other questions?
Any questions? All right, let's take Eric. If there's any more pizza, take it, feel welcome, take it back to your dorm, be the hero of your dorm. Have a great weekend. Next week, I'll be with Matt, will be speaking.
Okay.
Yeah.
All right, have a good weekend, y'all.
Sorry, I give it the,
Oh, the gap.
yeah,
Yeah,
that's what.
that's